But that's good. No, that's a good definition. Other people say it's greater than 1 and it has no factors except 1 in itself, or else it has exactly 2 factors. What can you say about if A, let's call it P for prime, it feels more like a prime number if we call it P. What can we say about phi of P if P is prime?
It's P minus 1.
It's P minus 1. And I've got down here as exercise for you to work out properties of this phi function, which will enable you to work out from the prime factorization of a number what is its phi value. Another interesting property of primes, which is perhaps not so obvious, is that if P is prime, then if P divides a product, P divides one of the factors, M, or P divides N. See, I'm trying to avoid that notation, or P divides N. That's another definition. In fact, the normal definition about not having factors other than, or a certain limited number of factors, is sometimes used, that property is sometimes described as irreducibility. It can't be broken up into smaller factors. And this property is sometimes used as primeness. That if it divides a product, then it divides one of the factors in the product. And if you think about a prime number dividing a product, it means you can't split the number so part of it goes into the M and part of it goes into the N. It all has to go either into the M or into the N. And so it sort of sounds like primeness. And it's interesting to compare it with the property of irreducibility, or what we normally think of as primeness. And it's another little exercise. This is actually a stronger property than irreducibility. So that if something has this property, then it has no factors. And these are little exercises that are there. If it has this property, then it is prime in the sense that you know it, that's to say, it's irreducible. And the converse is true only because of the fact that the greatest common divisor can be expressed as a linear combination. So that's an exercise that I've given. And it turns out that you get, in some of these other number systems that I would like you to investigate for yourself, you might have primeness and irreducibility don't necessarily coincide as they do in the integer. Now I want to do a little digression for a while. Go back right where we started with improper fractions and mixed fractions, and do the Euclidean algorithm in that way. And so in that way we would have A over B is Q plus R over B. And then the next state would be B over R, that was Q1 if you like, would be Q2 plus R2 over R, could be R1 if you like. And so on and so on. So writing it like that, what is the procedure now? Really, we've taken a number, we've written it as an integer plus a fraction, because remember R1 was less than B, so that's an integer part and a fractional part. So all we've done is taken a number, split it into its integer part and fractional part. Then what have we done at this stage? We've inverted, we've taken the reciprocal of the fractional part, and written that as an integer plus a fractional part. And what we've done once, we can continue, and so we can repeat this. But what is interesting about this is, Why does it matter that we started off with a rational number? We could start off with any real number and write it as an integer part and a fractional part. So we could start with any old number alpha and write it as, I'm going to use slightly different notation, a0 plus alpha naught, where a0 is an integer and alpha naught is between 0 and 1. Then take the reciprocal, write it as a1 plus alpha 1, take the reciprocal, and so on and so on and so on. So it's just doing the Euclidean algorithm, but now we're not restricted to integers or rational numbers. We can do it to any real number we like. In fact, we could do it, well, you could do it in other number systems, though you'd have to be a bit careful with some. And this procedure is called, anybody met this procedure before? This is called continued fractions. This is called a continued fraction because so dot, 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 dot. This is called a continued fraction because we can substitute for alpha naught. We can put this alpha naught, substitute for each equation into the one after that. And so we could write our original alpha, starting at the top, is alpha is a naught plus 1 over alpha naught. Now invert the second line and substitute that. Alpha naught is a1 plus 1 over alpha 1. Sorry, alpha 1. It's a1 plus alpha 1. Sorry, that 1 over a1 plus alpha 1. Now we can substitute for alpha 1. We know what 1 over alpha 1 was, so alpha 1 is 1 over plus alpha 2. These lines have to get very long. And we can go on. Alpha 2 is 1 over a3 plus alpha 3. And so we can continue that fraction, and that's why it's called a continued fraction. Now, continued fractions is a huge subject. I could spend the whole time available on continued fractions alone. But I'll just tell you some things, and I've got a few exercises for you to investigate. What happens if alpha is rational? It must terminate. We know that there will be a zero remainder at some stage. Alpha 2 is basically the remainder. So the procedure stops after a finite number of steps. It terminates if alpha is rational, if and only if. And it goes on forever if alpha is irrational. Remember, these are all integers, and so when you take them, you will have these a's are all integers. So if alpha is irrational, the only place you can have an irrational must be in the end. So if alpha itself is irrational, then all the alphas will be irrational, and therefore the procedure goes on forever. One of the interesting things about continued fractions, if you start with let's say, in particular, an irrational number alpha, suppose you know the procedure goes on forever, but if you just decide to stop at some point and say, okay, let's stop there, I won't be exactly right, it will only be approximately equal now. But this, now I could tidy up that messy continued fraction, finite continued fraction on the right-hand side, I'd get a rational number. And I'd get a rational approximation to alpha. And it turns out this procedure of finding rational approximations by terminating or truncating, cutting off an infinite continued fraction, is the best, the most efficient method for finding rational approximations. It can be proved that that's the most efficient method for finding rational approximations to an irrational. And that's how I happened to discover this one for pi. And I've given you some examples about leap years and all sorts of things, using how one can use continued fractions to get accurate approximations to irrational numbers. Possibly irrational numbers. No one never ever knows whether the exact length of a year is a rational or irrational number of days. But for getting accurate rational approximations with as small a denominator as possible. Obviously, if you don't restrict your denominator, you can just use a decimal approximation. But the whole purpose is to try and get a rational approximation with the smallest possible denominator, the most accurate, say, given a bound on the size of your denominator. Well, my 6 o'clock limit is approaching fast. I wanted to talk briefly about modular arithmetic.